There is one more equation I do want to talk about, though, one related to work. So we talked a little bit about units for what a joule is. It's a Newton meter. Work can also be defined as a force applied over a distance. And where this comes from, you can hopefully see it in terms of the direction. So I'm going to write the equation out. This is the other equation we're going to be working with work. Sorry, bad joke. Equals the force, and this would be applied force onto the object, or in technical cases, the net force on the object, because it's going to change its energy. Dot the distance over which it's applied, and this is a dot product. So for those of you mathematically unfamiliar with what the dot product is, it's the force times the distance times the cosine angle between the two. So FD. I'll explain what that means in a second with an example. So let's go back to our crate sitting on the ground. This was, I think we had 10 kilograms from the last example. Oh my goodness, the horizontal lines. Sorry, guys. Okay, pretend that's completely horizontal and flat. And let's not worry about friction in this context, okay? Because this really will be net force acting on the block. I want to pose a question, would be if I want to push the block and I want to push it going to the right. So let's say I want it to go right here. I want to move the block to the right and I want to move it right here. In terms of the case of where I should apply my force to the block, right here at spot 1, in the direction at spot 1, is that the best case? Right here at spot 2, right straight down at spot 3, right straight here, this is spot 4, and right here lastly at spot 5. I'm going to push the block and I want it to get to this spot right here where it says here. I'm going to push at spot 5. I'm going to push in the direction of where I want it to go. This is what the dot product in work, the work distance, work-force distance relation is. This is where the dot product is. What the dot product says, because cosine, so for those of you rusty in your trig days, cosine is maximized at a 0-degree angle. The cosine of 0 is 1. You can think of the cosine acts as almost a percentage of the force being applied to optimize work. You can think of it as optimizing the work or force you put into a system. If I want, because we human beings tend to be kind of lazy, we want to do the least amount of effort for the most reward, right? That's just human nature. So if I want the block to move to where I designated here, I want to push in direction 5 because intuitively my body knows that's going to be the easiest way to get it there. I know if I push at position 3, it is not going to go anywhere, right? I'm just pushing it into the ground. I'm not going to win a battle with the ground in that case. I'm not strong enough for that. Where this comes from mathematically, cosine function is, if I'm pushing straight down in the direction that it's moving, so hopefully I can draw it like this. This makes a right angle to the direction it's going to move. Cosine of 90 degrees is 0. So it completely negates it. It cannot be perpendicular to where I want it to move. And our bodies kind of know that. I'm not going to push perpendicularly to where I want something to go. I push in the direction I want it to go. So that's kind of the idea behind that. The next thing I wanted to talk about is if I were to push down at an angle, like let's say it's at spot 4, I know it would probably start to move a little bit towards the here, but it'd be a lot harder for me. I'm making more work for myself than I need to, right? Because I'm not optimizing my force. So where this comes from is I'm optimizing my force when I push in the direction of motion. Because at position 5, I'll try and draw this correctly here. So this is the box. I'm pushing this direction, and it's also moving in this direction. The angle between those two, it's hard to see because they're right on top of each other. The angle between them is 0. I'm directly aligned in the direction I'm pushing, right? If I push directly opposite it, well, that's an angle of 180 degrees. Cosine of 180 degrees is -1. So it would go the opposite direction, right? Which is not what I want, which we can kind of intuitively know that. So we can kind of pose a few questions here, and maybe I'll keep the same diagram up here. When I say, let's say we apply the force, let's keep our force constant. Let's say we want to do 20 newtons of force applied to this block. At position 5, what the equation for that would look like, and we're going to say, I'm going to specify the angles here based roughly on where it would be around the actual unit circle, but you don't need to necessarily know that. The angle at 5 is going to be our 0 degrees because it's directly in line with the direction I want it to go. The work then is equal to the force times the distance times the cosine of that angle, which in this case, it's cosine of 0, which is 1. It's maximized at 0. The force would be the 20 newtons. And let's say I'm pushing it over a distance. Let's say that this distance here is 3 meters. Okay. It's being pushed over a distance of 3 meters. So this is 20 newtons. This is 3 meters. Cosine of 0, which is just 1. This is going to give me 60 joules. That's how much work is done on the box in option 5. And I want my work to be maximized from my force, right? The most amount of work for the same force. That's the idea of optimizing work. So we'll do the same thing again with the next one. Let's look at option 4. So this would be, that should be the number 4. The angle theta would be 45 degrees. Where this comes from is here's the block. I'm pushing, it actually would be down this direction. This is the direction of my applied force. And then this would be the direction of motion. That doesn't look exactly like 45, but that's what I'm meaning. I'm just scaling it wrong. So this would be applied force, and then this would be the distance it's traveling, right? So that's our 45 degrees. Then in this case, it's going to be the work is equal to 20 newtons, 3 meters, times cosine 45, which we could actually calculate or plug in our calculator, but I'm familiar enough with unit circle that I know this is 60 times root 2 over 2 joules, which simplifies. I can call this 30 root 2 joules, but we see that it's less. It is significantly less than 60, right? So I'm not optimizing my force to my work as efficiently as I could have. At option 3, the theta angle is 90 degrees. So work is equal to FD cosine 90. But because cosine 90 is 0, anything times 0 is 0. So no work is being done when I push at option 3. Option 2 is, this one is actually at 135 degrees. So theta is 135 degrees. This would be the distance I want it to go. This would be the direction of the push, right? So this is the 135 degrees. This is the distance. This is the force. This would be the work would equal FD cosine 135, which I'm familiar from the unit circles, just this but negative. So it would be negative 32 joules, which is really not helpful for me. It's going the opposite direction. And then if I were to do it at 1, I would get cosine of 180, which would just give me, so at 1, I would get this number but negative, right? So it would be work equal to FD cosine 180. That's just negative 1. So it equal negative 60 joules. So really not helpful. So kind of can see this optimization is I will apply work in the direction I want something to go because of this dot product here. The math takes care of it for that. But hopefully you get a little bit of an understanding as to what the dot product is actually doing.